Imagine a global scene where tons of lithium emerge from the bowels of the Earth like a precious treasure. In the last few weeks alone, China has announced incredible discoveries. 1 million tons near Everest and another 1.3 million in Hunan. Sounds like enough to fuel an electric revolution for decades, right? But while the world chases this wealth, Elon Musk is going in the opposite direction, like someone who already predicted the collapse of the lithium game. In Tesla's Austin lab, quietly, a new type of battery is being forged, and it has nothing to do with lithium. It's the bold and almost unbelievable aluminum-ion battery, a technology that promises to disrupt the entire global electric vehicle supply chain. Tesla's new proposal may seem like a risky move, but the logic behind it is unbeatable. Lithium is rare, expensive, flammable, and concentrated in the hands of a few. Aluminum, on the other hand, is cheap, abundant, safe, and can be processed in the United States. Simply put, Tesla is trying to trade a gold rush for a can mine. But it's not a case of trading 6 for half a dozen. The aluminum battery is not just an alternative, it's superior. Elon Musk knows that if he wants to offer an electric car under $25,000, he can't rely on a resource controlled by the Chinese government. Within Tesla, the aluminum battery is already showing surprising results. With an energy density 3 times greater than that of a traditional lithium-ion cell, it promises to revolutionize the way we understand range, weight, and durability in an electric car. While current batteries require several complex components, aluminum allows for a simpler, lighter, and more efficient construction. For the average consumer, this translates into fewer stops for recharging, a longer lifespan, and lower maintenance costs. But for Tesla, this is more than just savings. It's industrial independence. The issue of dependence is, in fact, the most delicate point in this equation. Today, more than 60% of the lithium refining chain is in the hands of China. This means that any geopolitical tension, embargo, or trade war could completely destabilize electric vehicle production. And that's exactly what Elon Musk decided to anticipate. Tesla no longer wants to be at the mercy of the global lithium market, its speculative bubbles, and its logistical bottlenecks. By investing in aluminum, the company not only escapes the Chinese trap, but also positions the United States as a sovereign battery production center. But this game changer isn't just about patriotism or convenience. Aluminum offers technical advantages that are hard to ignore. It allows for ultra-fast charging, greater thermal stability, and a lower risk of fire. At a time when battery safety has become a critical issue, Tesla may be offering an elegant and functional solution. It's almost as if the company is trading the Cold War engineering of lithium for something cleaner, more efficient, and more futuristic. And this, of course, has profound implications for the future of electric cars, especially the highly anticipated Model 2. This model, which has been dubbed the iPhone of electrics, could become the first mass-market car with a range of over 600 miles, a recharge time of less than 10 minutes, and an affordable price even for those who've never considered driving a Tesla. But what few realize is that this feat won't come solely from the bodywork or onboard artificial intelligence. The real revolution lies beneath the car's floor, in the battery. And if that battery is indeed made of aluminum, we're talking about a structural change, not just a product change. While competitors are still stuck with lithium, fighting over supply contracts, and paying dearly for every refined ton, Tesla may be blazing a completely new trail, one that ignores the rules of the current game and writes its own terms. This explains why so many experts are paying close attention to what comes out of the Austin lab. They know that if this technology works, the game will change, and those stuck with lithium will be left behind. Fast. All this activity puts Tesla back at the center of the technology debate, not as a car manufacturer, but as a systems developer. The aluminum-ion battery isn't just a new piece on the board. It could be the entire board. And if it's truly integrated into the Model 2, the company could be delivering not just a new car, but a new way of thinking about electric mobility. The world is watching, but the curious thing is that no one seems ready for what's coming. Tesla's 4680 lithium-ion batteries were once considered an impressive feat. They offer an energy density of 250 kWh, generous range, and enough power to propel heavy vehicles like the Cybertruck from 0 to 100 km/h in just a few seconds. However, behind this efficiency lie significant technical limitations. They are heavy, constructed with multiple layers of expensive materials, and still rely on fragile elements like graphite, nickel, and cobalt. Each cell is like a small metal safe that requires constant protection against overheating and internal failures. And this is where aluminum emerges not only as a competitor, but also as a natural substitute. The secret of aluminum lies in its structural simplicity. While the 4680 cell is a stack of components, with layers of copper, steel, and active materials, the aluminum cell can be molded into a single solid block. This block functions simultaneously as a cathode and a conductive structure, eliminating intermediate parts and drastically reducing weight. The consequence is clear: less dead mass and more space dedicated to real energy storage. The practical result is a lighter, more agile car capable of traveling more kilometers with the same amount of charge. Another determining factor is safety. Lithium batteries suffer from the problem of dendrites, small metallic formations that, over time, can penetrate the cell's internal separator and cause fatal short circuits. This is where the risk of fires and explosions arise in some electric vehicles. Aluminum, on the other hand, does not face this same problem because it uses an ionic liquid electrolyte, a dense solution of stable salts that is non-flammable. This material continues to operate stably even at temperatures above 200 degrees Celsius, something lithium could never achieve without compromising safety. This increased thermal stability also eliminates the need for complex cooling systems. Currently, 4680 batteries require cooling tubes, special fluids, and reinforced separators to keep temperatures under control. This adds weight and reduces the pack's efficiency. With aluminum, Tesla can eliminate up to 70 or 80 kiloliters of these support systems, focusing energy directly on the cell's active material. In other words, instead of carrying parts that merely ensure safety, the car now carries only useful energy. Aluminum's energy advantage also cannot be ignored. Each atom of this metal is capable of carrying 3 electrons, while lithium can only carry 1. This seemingly simple difference multiplies the cell's potential and allows for densities between 200 and 300 kWh, while lithium is typically limited to 160 and 180 kWh. In simple terms, for the same battery mass, an aluminum battery stores significantly more energy, extending range and reducing the need for large, bulky packs under vehicle floors. In real-world use, this difference can transform the driver's experience. Imagine a car that not only offers more range, but also requires less downtime to recharge and conveys greater confidence in terms of safety. There's no constant anxiety about whether the battery will degrade over time or whether unexpected overheating could cause serious problems. This mental relief carries as much weight as the technical numbers, because the consumer isn't just buying efficiency, but also peace of mind. Furthermore, structural simplification paves the way for faster and cheaper production. Each 4680 cell requires multi-part welding, heavy-duty metal treatment, and strict controls to avoid microscopic flaws. Aluminum cells, on the other hand, can be manufactured using more straightforward industrial processes such as block molding and simpler integration into vehicle platforms. This means lower labor costs, less waste, and greater scalability to serve millions of cars simultaneously. This superiority doesn't just mean Tesla will have a technical advantage, it changes the balance of power in the industry. While other manufacturers are still chasing lithium supply contracts and trying to perfect their own versions of cylindrical cells, Tesla may be about to leapfrog an entire technology generation. This shift in performance wouldn't just be a performance issue, but a watershed moment that separates who will lead the electric transition from who will be left behind. By switching to aluminum batteries, Tesla is able to do something that seemed impossible: completely redesign the structure of its electric vehicles. The traditional battery pack, previously composed of hundreds or thousands of cells, organized within a metal case with multiple layers of protection, can now be replaced by a single block, molded with millimeter precision. This new approach eliminates the need for individual cell assembly, as the aluminum block itself acts as both an energy structure and a physical support. And this seemingly technical detail changes everything in the manufacturing process and the car's final performance. This new aluminum block can be stamped using Tesla's gigantic machines, the famous Gigapress, which have already revolutionized chassis assembly in models like the Model Y. With the new battery, Tesla integrates even more components into a single piece, cast directly into the vehicle's floor. This increases the car's structural rigidity and reduces welding and fitting points, which are vulnerable to collisions and vibrations. This simplification not only improves production efficiency, but also the vehicle's safety and durability over the years. And the weight savings, in this case, aren't just symbolic. An aluminum battery pack can shed about 88 pounds in the housing alone, representing a reduction of approximately 11% in the total weight of the assembly. This has a direct impact on the car's energy efficiency. Less weight means less rolling resistance, better acceleration, more responsive braking, and, of course, greater range. Tesla is literally trimming fat from the system, and this results in more performance with less mechanical effort. Another interesting point is that the absence of the traditional battery box frees up interior space and optimizes mass distribution. Without the need for metal reinforcements and heavy protection systems, the battery integrates into the chassis as a living part of the car, rather than as a foreign body embedded underneath. This opens up opportunities for new interior designs, more space for occupants, and even potential innovations in suspension or storage systems. In terms of cost, the impact is also enormous. A traditional battery requires several processes: cell assembly, contact welding, insertion into protective molds, installation of thermal sensors, and so on. With aluminum, many of these stages are eliminated. The result is a shorter assembly line, with fewer steps and less chance of failure. This translates into faster production and cheaper vehicles, essential for the Model 2 to truly position itself as an affordable electric vehicle in the global market. Maintaining these cars becomes simpler. With fewer moving or fragile components, the chances of failure drop dramatically. Instead of dealing with loose welds, failing sensors, or modules that need to be replaced as a whole, owners of a Model 2 with an aluminum battery will have fewer headaches and greater long-term reliability. This is a significant factor in the purchasing decision, especially for those purchasing their first electric car and still concerned about durability and technical support. This structural efficiency also allows Tesla to rethink how it distributes the car's internal resources. The weight and space savings open up space for new autonomous systems, optimized cooling, improved sound insulation, or even innovations yet to be revealed to the public. The battery is no longer an isolated component, but an integral part of the vehicle's architecture, like the skeleton of a living organism that simultaneously powers and sustains everything. Ultimately, what seems like a technical detail could prove to be the key to the Model 2's success. Elon Musk isn't just launching a new car, he's redefining what's possible when you rethink the entire logic of an electric vehicle. And by transforming the battery itself into part of the chassis, Tesla is telling the market that it doesn't just want to compete, it wants to lead, setting the standards for a new automotive era. With the structure and design already optimized, The equation that weighs most heavily on the consumer's wallet remained to be solved: the final cost of the car. And this is where aluminum shines again. This metal represents about 8% of the Earth's crust, making it one of the most abundant resources on the planet. Compared to lithium, which is location-dependent and highly affected by geopolitical crises, aluminum offers a stability that the automotive industry has been craving. Furthermore, the cost of raw aluminum is only around $2,500 per ton, a figure that dispels any argument that advanced batteries need be expensive. But the magic isn't just in the price of the raw material, but in what it eliminates. An aluminum battery pack requires far fewer welds, fewer components, and fewer expensive manufacturing processes. Tesla estimates it can shave 150 kiloliters off each pack and reduce labor with 60% fewer joining points. This alone saves each car about $1,900, a difference that multiplies quickly when you consider mass production. Now imagine that applied to hundreds of thousands of Model 2s rolling off the assembly lines. And there's more. Unlike lithium, whose refining chain is dominated by over 60% of China, aluminum can be mined, refined, and processed directly in the United States. The U.S. has over 300 million tons of bauxite reserves, particularly in Arkansas, Texas, and Georgia, as well as stable partnerships with Canada and Australia. This allows Tesla to build a local production chain from extraction to final assembly, without relying on international transportation, import taxes, or external political instability. This geographic independence is a strategic victory. With escalating trade tensions between the U.S. and China, relying on lithium batteries has become a risk no manufacturer wants to take. Even more so now that the U.S. government, under its new industrial policy, is strongly encouraging domestic production with subsidies, exemptions, and tax credits. By focusing on aluminum, Tesla not only avoids these risks, but also fits perfectly with the goals of the IRA, the Inflation Reduction Act, guaranteeing tax and logistical advantages. The final impact of all this? A battery that used to cost $8,600 can now cost just $3,900. This savings of nearly $5,000 per unit is what gives Tesla the leverage to sell the Model 2 for less than $25,000 and still maintain profit margins. And that's without factoring in additional incentives. With the $7,500 federal credit offered to locally manufactured electric vehicles, plus the company's seasonal promotions each quarter, the Model 2's final price could plummet even further. Realistically, an American consumer could park a Model 2 for between $11,500 and $12,000. This figure already takes into account all discounts, incentives, and reduced manufacturing costs. For many, it will be the first time an electric car has become a truly affordable option, not just in the automaker's language, but in the practicalities of monthly financing. And this isn't just a number that impresses consumers. Market analysts, investors, and competitors are paying close attention to this trend. A vehicle with increased autonomy, a simplified structure, and a drastically lower cost